Hi, my name is Michael Tapaneka, and today I will be presenting the Splay tree data structure. Splay trees are nearly balanced self-adjusting binary search trees that were created in 1985 by Daniel Dominic Sleater and Robert Andre Tarjan. It performs three basic operations, such as insertion, search, and deletion. Each of these three operations will involve a splay. The splay allows the tree to balance itself by moving the element that will be searched, inserted, or deleted to the root of the tree without breaking the binary search tree invariant. Splaying an element is the process of bringing it to the root position by performing suitable rotation operations. Splaying elements will bring more frequently used elements closer to the root of the tree so that any operation on those elements is performed quickly. There are 6 rotations used to splay any element. There are zig rotation, zag rotation, zig-zig rotation, zag-zag rotation, zigzag rotation, and zag-zig rotation. The zig and the zag rotations are used when the node has a parent but no grandparent. Zig rotates the node to the right and zag rotates the node to the left. In the first example, we are using a zig rotation of splay node 3. Node 3 is rotated to the root, node 5 becomes its right child, and node 2 stays as its left child. Node 5 still has node 6 as its right child, and node 4 becomes node 5's left child. In the second example, we are using a zag rotation to display node 5. Node 5 is rotated to the root, node 3 is its left child, and node 6 is its right child. Node 4 is rotated to the left and becomes node 3's right child. The zig-zag and zag-zag rotations are used when a node has a parent and a grandparent. The zig-zag rotation rotates all nodes twice to the right, and the splayed node is typically the left child of a left child. The zag-zag rotation rotates all nodes twice to the left. The node splayed here is the right child of a right child. In the first example, we splay node 2. In the first rotation to the right, node 3 moves to the root, node 2 is its left child, and node 5 is its right child. Node 5's right child is still node 6, but because of the right rotation, node 4 is now node 5's left child. In the second rotation to the right, node 2 moves to the root, and every other node shifts once to the right. In the second example, we splayed node 6. In the first zag rotation, node 5 moves to the root, node 3 becomes its left child, and node 6 becomes its right child. Node 3's left child is node 2, and its right child is node 4. In the second zag rotation, node 6 moves to the root, and node 5 becomes its left child. Node 3 is node 5's left child, and node 3's children are still nodes 2 and 4. The zigzag and zag-zig rotations are also used when a node has a parent and a grandparent. The zigzag rotation is every node move once to the right and then once to the left. The zag-zig rotation has every node move once to the left and then once to the right. In the first example, we are splaying node 4, which is the left child of a right child. This node rotates to the right and becomes node 3's right child, and in the process, node 5 becomes its child. Node 6 is still node 5's child, and node 2 is still the root's left child. After the zig rotation, the zag rotation moves node 4 to the root, node 3 becomes its left child, and node 5 becomes its right child. In the second example, we splay node 4, which is the right child of a left child. After the initial zag rotation, node 4 becomes node 5's left child, and node 3 becomes node 4's child. With the zig rotation, node 4 rotates to the root, node 5 becomes its right child, and node 3 stays as its left child. Why splay trees? Splay trees are simpler to implement than other self-balancing binary search trees and are simpler to code when compared to AVL and red-black trees. Splay trees are also unique in how rotation is necessary even during read-only operations, such as search. Also, splay trees require less space as no balance information is required. Splay trees are commonly used to implement caches and for data compression. In the real world, splay trees are used in network routers. The data structures that are the most similar to a splay tree would be AVO and red-black trees. Each of these trees will try to balance themselves when certain criteria is met. For the AVO trees, if the heights of the left and right subtrees of the root differ by at most 1, the nodes will rotate. A red-black tree will attempt to balance itself by splitting nodes to be either red or black, having the root and leaf nodes be black, having no two red nodes touching, and for every path from root to leaf nodes to have the same number of black nodes. Essentially, you use splay trees when you're looking for fast access to recently used items. You use red-black trees when operations like insertion and deletion are more often used than the search operation, and you use AVO trees when the search operation is more frequent than the insertion and deletion operations. Time complexity. Most of the operations have a amortized order log n time complexity on average. The worst time complexity would be theta n.